Hi everyone! In today's video, we are going to go through IChO 2024 question 6. So this is an organic synthesis problem, and our target compound is penicillin DK, so that's this molecule shown here. So question 6.1 is about assigning stereochemistry to the chiral centers. So let's see what the question asks us to do. So first, we have to mark the stereocenters, and then we have to assign RS conventions to them. So let's spot all the chiral centers first. So chiral centers are carbons with 4 different groups attached to them. So this is 1, 2, and 3. So there are 3 chiral centers in total. And then let's label them R or S individually. So let's start with this carbon. So so we know that the hydrogen is pointing in. So hydrogen is our least priority group, so it's pointing in, so we are in the right perspective for things. So the first priority is of course nitrogen, because it's heavier than carbon, and then because this carbon is attached to oxygen while this carbon is attached to carbon, we know that this carbon is of a higher priority, so let's label it priority 2, and this carbon is priority number 3. While hydrogen is priority number 4. So we know that the priority groups actually go this way, so that is clockwise, and that's why this chiral center is an R. Okay, let's now move on to this chiral center. So here the least priority group, which is hydrogen, is pointing outwards. So that's we're not in the right perspective, and we need to rotate the molecule by 180 degrees. But we don't need to redraw the molecule. Let's just assume this hydrogen is pointing in first, and then we just have to turn clockwise into anti-clockwise or vice versa after we are done with the assignment. So the first priority is of course sulfur, because it's heavier than both nitrogen and carbon. And then the second one is nitrogen, while the third one is carbon. So here the priority goes in an anti-clockwise fashion, but we know that this hydrogen is pointing out, so we need to shift our perspective. We need to rotate our perspective by 180 degrees, and so the priority groups actually arrange themselves in a clockwise fashion, and that's why this chiral center is also an R. And then let's move on to our third chiral center. So our third chiral center is this one, and we see that it's attached to a hydrogen that's pointing out, so we need to take note of that. But we can do the same thing as we did for this chiral center, which is to assume that a hydrogen is pointing in first, and then nitrogen would be the top priority, and followed by this carbon here, because it is attached to followed by this carbon here, because it is attached to an oxygen, which is of a higher priority than nitrogen. So this is our second priority, and this is our third priority. So we see that it is going in a clockwise fashion. However, because this H is pointing out, we need to rotate the molecule by 180 degrees, and that is why the actual it's the priority groups are going anti-clockwise, and that's why this is S. But one good way to remember S is S in R is S is kind of sinister, right? So it is going anti-clockwise, so it is going against the clock, so it's sinister. So that's how you do 6.1. 6.2 is quite simple as well, because it is just to calculate the total number of possible stereoisomers, and we know that there aren't any CC double bonds here, so we don't need to care about the easy isomers, so we only care about all the enantiomers each chiral center give rise to, and there aren't any like symmetry in this molecule, so we know that the total number of stereoisomers is just going to be 2 to the power of 3, which is the number of chiral centers here, and each chiral center gives rise to 2 different enantiomers. So in total, we have 8 possible stereoisomers. Okay, now the next part of the question has to do with the synthesis scheme. And let me just slowly scroll down to show you the scheme. And you can just pause here to work everything out, and then you can listen to my explanation after you have worked everything out. So we are given this scheme, then we're given some questions here, and we're also given some hints here. So let's first take a look at the questions to have an idea of what we're doing. So 6.3 asks us to choose suitable reagents for the steps 1 to 4. So steps 1, 2, 3, 4. For these steps from this list. And 6.4 is basically deducing all the lettered structures in the scheme, while 6.5 and 6.6 are just selecting rows of the reagents, which we can do later. So let's take a look at the hint and how they help us. So to remind us of the hint, we can just briefly label them beside the structures so we don't forget that we actually have these hints. So compound A contains two signals that each integrate to 3 hydrogens. So let's label compound A, so 2 signals, each 3H. Of course, it contains other signals, and both of these are doublets. And then compound A and D are open chain, so open chain, while compound B and E each have a 5-member ring in addition to any rings in this group. And this is actually a clue for us that either B or E or both contain this group. So B is here, so we know it's a 5-member ring. And E is also a 5-member ring. And also we see that the thing before E has this group, so this group carries over to E. And also this compound is used for chiral resolution, and we need to look for this compound. It is actually here. And also they give you the structure, but there's no way you can tell what it does just by looking at the structure, or at least I can't. So we're just going to write down chiral resolution here. So with that, we don't need to care about the hints anymore, so we can just focus on these 2 pages. Yeah, because you have so many pages, so sometimes it's important to organize and present yourself the information in a way that you're most comfortable with. So let's go on to 6.3. So we're supposed to choose suitable reagents for the numbered steps on the answer sheet, which seems a bit difficult because sometimes, for example, for step 3, you don't know the previous compound, you don't know the next compound. So how are you supposed to know which reagent is suitable to convert from an unknown to an unknown? Well, let's just work through it step by step, okay? So in step 1, we see that we have the insertion of this sulfur here, which isn't present in this compound. So we know that whatever reagent given here must contain a sulfur in order for step 1 to work. So what are our options? Our options are B and F. So these are the only sulfur containing compounds. And then we can make a guess of what happens from this compound here to this compound here. Well, we see that we used to have a conjugated carbonyl group, and after that the sulfur appeared here, and then the conjugated group becomes unconjugated, and also your ring kind of opens up. So we know that a conjugate addition has happened. So we need a nucleophile, and a very obvious choice here is this option F, because it has a nucleophile, it has your sulfur here, and then you have your solvent, and then you have your ring hydrolysis step. So it fits the description really well, so we know that step 1 is going to be F. And you can write it down in our answer sheet, don't just label on a question paper. So yeah, so step 1 is option F. Now let's take a look at step step 2. So step 2 goes from B to C, and we are actually not completely sure what step 2 is at this stage, because we don't know what B is. But we can we can just take a look at the other steps first, and just do this by elimination, or after we have elucidated compound B, we can come back for step 2. So let's take a look at step 3. So step 3 goes from from C to D, and we actually have C here. This plus just means it's one enantiomer of the racemate mixture of C. So it's just, the structure is going to look like this. It's just going to have one enantiomer only. So from this compound to D, we see that we go from a 5-member ring to an open chain compound, and that means this ring somehow gets opened, and the weakest point of the of this ring is definitely this part, which resembles an acetal, and we know that acetal can get hydrolyzed, and after it gets hydrolyzed, it will basically this sulfur and nitrogen will be exposed again. So we know that an acetal hydrolysis probably happened, or acetal-like hydrolysis. So we need to find a reagent that can give you the hydrolysis reaction that is similar to acetal hydrolysis. So some obvious choices are A, C, and yeah, that's it. But we know that acetal hydrolysis cannot proceed under basic conditions, so it has got to be acidic condition under acidic conditions. So step 3 is done with option A. So it's a 2 molar hydrochloric acid, and so we have chosen both A and F. And then let's take a look at step 4. So step 4 goes from a 5-member ring to a 5-member ring. So we know the ring didn't get opened. Well, probably not. And then we know that compound E has this group. So this group didn't go, still persists in compound E, but this group went away afterwards. So we know step 4 is probably to remove this protecting group. So something happened in step 4 that removes this group. And another very jarring clue is that we have a HCl here. So step 4 needs to contain HCl somewhere. And we see that we actually have two options that contain HCl, which is option A and option E. However, the reason the answer is going to be option E is firstly because option A is already taken. But even if you don't know whether you can choose the same option again, you know that this is a really complicated group here. So you wouldn't logically expect something as simple as 2 molar HCl to just make it fly away. And you can also recognize this group from your Gabriel synthesis of amines, and you know that this N2H4 is going to do nucleophilic acyl substitutions here and remove this group from your amine. So this is your amine, and so you know that this is the appropriate compound. And if you know Gabriel synthesis, then this part is really straightforward. But if you don't, I think it is also quite reasonable for you to pick option E because there are simply no better options around. So yeah, option E is your best choice here. And then we are left with these three options for compound 2. Sorry, for step 2. But at this stage, even if you don't know what what your choice should be, you know that it's probably not going to be B because it has the SO3H2SO4, which is kind of like a really concentrated version of the sulfuric acid. And you know this option is probably here to confuse you because this has sulfur and this has sulfur, so it's probably here to confuse you about what to choose for step 1. So this is probably a distractor, so you don't need to care about this option. And then you are left with two other options, which is your NaOH and your formic acid. And you see that from this compound to this compound, actually the part that gets changed other than the ring, and we know the ring didn't react, is this part. You have different things attached to the nitrogen. So the thing that's newly attached probably comes from step 2. And if you draw out the structure of formic acid, which is this OH and H, you see that if you acyl substitute this OH away and you replace it by the nitrogen here, then this actually gives you your CHO group. So you know D is going to be your correct answer. And also you know that option C is not very reasonable because, well, you can't really expect a base to like completely change your compound given that you don't have any functional group that's very reactive with base here. And yeah, you just don't expect NaOH to actually be able to work in step 2. But we can just keep all our options here in mind, and once we work through the scheme, we can check whether each option is very reasonable or not. So change color. What color should I use? Okay, I'll just use this dark orange. So let's now go on to 6.4, which is to elucidate each of the compounds. So our compound A is formed by the reaction of this compound, which we know will probably act as a nucleophile because it has a really nucleophilic or basic N here. And then we know that this is probably going to act as an electrophile either at this carbon or this carbon because both are electrophilic centers. And so the question is, where will this nitrogen attack? Will it do an SN2 reaction at this carbon or a nucleophilic acyl substitution at that carbon? So one thing we should know is that nitrogen is really hard. So and also this carbonyl group, this acyl chloride group is really hard as well, while this this saturated carbon is quite soft. Sorry, it jumped around. So while this saturated carbon is quite soft because here you have both oxygen and chlorine pulling electron density away, and oxygen is really electronegative, and here you only have one chlorine pulling the electron density away. So the polarity of the bonds for like the, let's say, electron deficiency of this carbon is much greater than an electron deficiency of the other carbon. So we know that this carbon is also quite hard, and it will prefer a hard nucleophile or a charge-dominated interaction, while this carbon here will probably prefer an orbital-dominated interaction. So we know that the lone pair on the nitrogen is going to attack here, and then it pushes the bond up, it pushes the lone pair down, and you make the chloride fly away. So compound A would just be this compound. And if you're not sure where you should attack, you can just go ahead and draw the other possible compound first, and then we can see which of these compound fits our clue here and also the subsequent structure. So let's draw the other compound just in case. Although this compound looks quite cursed because you have a nitrogen here and you have something that's really reactive here. So acyl chlorides really don't like to stay unreacted. So you know this is, like, you're quite sure this is going to be our correct answer. But let's just draw both first. Let's just say you don't know which one would be our correct answer. And then you can take a look at this structure and you see that there is a CN double bond here. So you know that this CN double bond probably comes from a CO double bond, and then the reaction happens and you have like nucleophilic acyl substitution with the loss of carbonyl oxygen. So you know that the carbonyl group is going to have to be next to the nitrogen, and that's why this gas is incorrect. So we know this will be our correct answer. So this is A, and then we know step 1 is your F. Option F is it's a Michael addition, so it's a conjugate addition. So you have your nucleophile attacking here and then push, and then when it comes down it pushes this away, and then you will get something like this. Yeah, so let's see what happens in this step. So in this step, you form a 5-membered ring, and let's draw out the structure of acetone so this becomes easier to see. And if you compare this structure with this structure here, you see that the part that really changed and that is consistent with the structure of acetone is here. So this is kind of like an acetal formation, and you can just draw out the structure here. So you know that the sulfur lone pair kind of attacks this carbonyl carbon, and then because you're doing it in acid, the first step is acid, right? So it makes this part fly away because you know this part is not present here, so the first part must be there for a reason. And with heating, which is quite harsh, you know, it probably does something quite important to the molecule, which is to make this part fly away. And so after this part flies away, you have a NH2 group here, which can also act as a nucleophile. And so so it would just make this carbonyl oxygen fly away after some nucleophilic additions, and then you will have this compound. So this part is your acetone. Because recall your acetal formation, so if you put your acetone in aqueous acid, then sometimes it will give you something like this, and the mechanism for this is quite similar to the mechanism for this. And then let's take a look at step how B transforms to this. Well, there's the addition of formic acid, so we know that a nucleophilic acyl substitution probably happened with formic acid as the electrophile and this nitrogen as the nucleophile. So that's pretty straightforward. Now, from a racemate mixture of C to a single enantiomer of C, we just undergo chiral resolution. But the plus here and the plus minus here, we don't know whether the plus correspond to R or S. Like, there isn't a convention that says like plus correspond to R, for example, so we can't just do that. Instead, we have to work backwards from now on because we don't know which sterol isomer this plus C is. So let's work backwards, and the next structure that contains part of D and part of C is this structure here. And so let's see what happens in step 4. Step 4 is E, so it's your, oh yes, it's to make this group fly away, right? So compound 4 would just be this, but with this group. So let's draw compound E. So that will be your compound E. And oh, you take one look and you're very happy because you see that this COOH group is the same as this COOH group. And you might just copy down the structure of C here with this COOH group pointing out. But that is incorrect because you see the sulfur is on top or the nitrogen is below here, but the nitrogen is on top and the sulfur is below here. That means the molecule was flipped 180 degrees. And that's why the COOH group is actually supposed to be pointing in if you copy down this structure. But a simpler way is just to copy down this entire thing into your D, because we know the other part comes from this. But yeah, so let's write down the single enantiomer of C. So this is actually supposed to be pointing in. And from C to D, we have a hydrolysis. And so your compound D will just be this. Yeah. Step draw compound D. Let's see. Yeah, so that will be your compound D. And yeah, so that's your compound D. And one thing, okay, how should I say this? Okay, we'll take a look at compound D again later. And we know that, yeah, we're going to take a look at compound D later. So we have worked out E. Now let's work out F. So what happened? Oh yeah, so let's say let's take a look at what happens between D and this new compound here. So we basically have another thing that's similar to acetal formation. So this is just the step that we have been repeating. And we can take a look at this compound, and you see something unusual that you don't see quite often in schemes, which is, or you might see it quite often, but you don't really do it much. So this is your HCl dot your amine. So that's actually a salt. And we can take a look at what step 4 is. And step 4 is this part E. And you see that when you add HCl, it actually forms a salt with the amine. So the question is hinting at you that you need to write down the salt instead of just the organic part. So that's what we're supposed to do for part D also, because you also add HCl to it. And that's why the correct answer is actually HCl dot your amine. So this is a salt. So you can imagine this nitrogen being protonated, and then you have your chloride counter ion there. So yeah. Now from this structure, we're going to move forward. So no more working backwards for now. And you can see that the part that changed from this structure to the final structure is basically this part. So there isn't a ring here, but there's a ring here. And we know the amine can do funny stuff on its own, so it does that. And so one of these two steps form the ring, while the other does the funny stuff on the amine. So the step that does the funny stuff to the amine is obviously this step, because you see the final structure here. So there's another, like, F is basically the nucleophilic acyl substitution product of this compound. So F will just be NH, and you have this. But you also know that after that you add a concentrated HCl and pyridine. So you don't just add stuff for no reason. They must have done something. And another thing that you can see here is that you have a really bulky thing here, like that's kind of protecting the carboxylic acid group. So like if you remove this, then you'll get back a carboxylic acid via hydrolysis. So as the hydrolysis, so that's what happens, because you know that you have to have a reactive thing that gets converted into this. Like you have to have a carboxylic acid that kind of allows the nitrogen to attack it and form this four-membered ring. So you know that the ester group is also hydrolyzed, and so you get an ester. Sorry, you get a carboxylic acid. And finally, in the last step, we have DCC. So DCC is this compound here, and anytime you see an N double bond C double bond N, it's quite likely to be a coupling reagent. So since it's a coupling reagent, we have the final compound, we know that it couples this part and this part of the molecule together. So it kind of just forces them to undergo a reactions, because under normal conditions, if you have like an amine and a carboxylic acid, they don't react because they just form a salt. So you need a coupling reagent to do the job. And DCC basically joins these two parts together. So it forces the whole thing to undergo a nucleophilic acyl substitution, and that will give you your final compound. With that, we are down to the final parts of the question, 6.5 and 6.6. And we already have the answer to 6.6, which is that DCC is a coupling reagent. And the role of acetone leading to step B is that it's an electrophile, because it undergoes nucleophilic acyl substitution. So, nucleophilic acyl substitutions with a loss of carbonyl oxygen, so it's an electrophile.